So if anyone cannot see the presentation, let me know. It should be visible to you now. Uh, I will get started. Perhaps some people will be joining a little bit later. Thank you very much for joining this webinar on heat integration and pinch analysis with Natural Resources Canada's integration software. I'm Michael Ross with RER Energy. This webinar will last about an hour. So at the end, there'll be an opportunity to ask questions if you have any. First up, I should acknowledge that a lot of the presentation materials I'll be going through today, as well as the software I'll be demonstrating, were provided by Natural Resources Canada, and in particular, the CanMet Energy Group in Varennes, Quebec. Today's presentation is going to consist of three parts. In the first part, I'll give a brief introduction to process integration, the benefits and results it's had in Canadian industry, as well as a little bit of an overview of the process integration approach and even some key concepts in process integration. There are people in the audience today who are already experts in process integration, and they may find this first part of the presentation a little bit less interesting. But what I think they will really enjoy is the second part of the presentation, which is an introduction to Natural Resources Canada's integration software. This is powerful, easy to use software that can be used both for pinch analysis, so a key part of process integration, as well as for examining heat recovery opportunities from utility systems such as steam systems, refrigeration, and compression systems. The last couple of slides are going to discuss what's next, how you can get the integration software, and further training opportunities that are available associated with this software. So why are people interested in process integration? What's the motivation? Well, when you have complex industrial processes that are using a lot of energy, certain questions naturally arise. These are questions like, what are the heat recovery opportunities in this plant? What heat recovery opportunities should be prioritized? And if you do one heat recovery opportunity, what effects might it have in terms of the potential for further heat recovery projects? And finally, the question may be, how close is the plant to achieving maximum heat recovery or equivalently minimum utility consumption? And that sounds like a pretty innocuous question, but it's actually very hard to answer if you don't use process integration techniques. Conventional energy audit techniques or energy efficiency techniques won't be able to tell you whether you've arrived at or how close you are to arriving at maximum heat recovery potential or minimum utility usage. Similarly, simulation techniques, although very powerful, can't give you that answer unless you can be absolutely sure that you've considered every possible configuration of the plant. And in a complex plant, of course, you cannot be sure of that. Process integration, on the other hand, can help us answer all these questions. And that's why people get interested in it. So what is this process integration approach? Well, it's a plant-wide approach that analyzes energy flows within an industrial facility to identify and correct inefficiencies within the plant. And it's different from more conventional approaches in that this global approach permits it to find opportunities that are missed when individual operations are considered in isolation. So a plant that has had a lot of energy audits and has had all the individual lines within the plant optimized, or even a new plant that's been built but not with process integration techniques, will typically have further energy efficiency savings or potential energy savings that can be turned up in a process integration study. Who can benefit from this process integration approach? Well, there are kind of two prerequisites. First, it has to be a plant with a certain level of complexity. If the plant is very simple, then standard conventional techniques will typically be sufficient to determine what energy savings are possible. By complex, I mean plants that tend to be characterized by several of the following aspects: numerous heating and cooling demands, many process heat exchangers, the inclusion of energy-intensive equipment such as dryers, evaporators, furnaces, kilns, reactors, or distillation columns, a heavy steam usage or hot water usage, or even a large refrigeration load. So the plant doesn't need to have all of those, but if it has a few of those, then that tends to be associated with um, a complex energy system that could benefit from process integration. The other aspect is that the plant should use a significant amount of thermal energy, because this is, at least as the usage of this tool, it's for heat integration, for uh, achieving energy savings in thermal processes. So if there is a lot of energy, thermal energy being used in the plant, then the potential for savings will be greater. So that's a kind of another prerequisite. Who's been using process integration in Canada? Well, these results are from Natural Resources Canada's incentive program for process integration studies. So they funded a total of 62 studies. In those 62 studies, about half of them were from the pulp and paper industry, and then about another quarter from the food and beverage industry. They only funded, for instance, about 5 studies in the petrochemicals industry, but that doesn't mean that the petrochemicals industry hasn't adopted process integration. It just means they weren't involved in Natural Resources Canada's incentive program. And we can see that reflected in the list of companies down the right-hand side that have been doing process integration in Canada. There are lots of food and beverage and pulp and paper plants listed there, but there are also like Chevron, Shell, and other petrochemical companies who have been involved in this. And what energy savings result from process integration studies? Well, it's going to depend on the facility, obviously. It's also going to depend on the sector. These are some findings from Natural Resources Canada. They've found in past work that typically savings of 10% can be achieved in a process integration study, and that may go up to over 30%. Particularly in the food and drink industry and the pulp and paper industry, very strong potential for energy savings has been observed. And these are energy savings associated with projects that have reasonably quick payback periods, so typically half a year to 3 years. So financially viable projects that can achieve 10 to 25 to 30% energy savings. In certain industries and at certain points in time, actually the energy savings may be less of a driver than simply the increase in throughput that can be achieved through improving the process with process integration techniques. So to give an example of that, a few years back, we taught a process integration course in Calgary, specifically for the oil sands industry and their SAGD, their steam-assisted gravity drainage process. And at that point in time, energy prices were very high, oil prices were very high, and the potential for 10 to 25 to 30% energy savings really didn't get the participants that excited. What did really get them interested in process integration was the realization that by improving the efficiency of their process, they required less steam, and they were constrained by the steam output of their once-through steam generators. So by improving that energy efficiency, they were actually able to increase the throughput of their existing plant. And for them, at high oil prices, that was a much more interesting way of looking at the same project. So these studies that can identify these savings typically cost, say, $40,000 to $200,000, but that's really going to depend on the facility. Well, what's in these process integration studies? What do they provide? Well, in short, they provide a list of prioritized energy savings projects organized in a clear plan. And this list can contain things like the following. First, best practices and operational changes. So these are, the standard application of the best practices and operational changes that would include things like elimination of water tank overflows, cleaning of fouled heat exchangers, improved control strategies, or set point adjustments. As a second thing, they'll include application of standard heat recovery techniques from utility systems, such as boilers, compressors, or refrigeration systems, or energy-intensive process equipment like dryers, furnaces, or evaporators. Now, so far, this is all stuff that you could find in a conventional energy audit or a conventional approach. Where process integration really distinguishes itself from conventional approaches is more in the third thing you'll find here, which is a really in-depth analysis of potential for process heat recovery. So using hot process streams that need to be cooled to heat other process streams, or recovering heat from effluents or using flash steam. Also, process integration studies will often identify water-saving projects that can lead to energy-saving projects. So, for example, the reuse of utility water as process water. And finally, often there will be cogeneration and heat pump opportunities identified within the process integration study. This arises naturally because the reduced process steam demand associated with the energy savings increases the potential for power generation from the existing steam plant. Or similarly, the potential to switch medium pressure steam to low pressure steam it increases the potential for power generation. And heat pump opportunities are often a part of process integration studies because the process integration techniques are very well suited for identifying the optimal use of heat pumps and where they should be placed and how they can be best used. What are the main steps in these process integration studies? Well, they are laid out here in steps 1 through 7, and I'll go through these quickly before spending a bit of time focusing on pinch analysis, which is kind of the key part of this. The first step is to have a simplified process flow diagram for the entire plant, ideally, or at least all the parts of the plant that will fall under consideration of the study. The second part is to come up with an energy and mass balance for all the components in that process flow diagram. We want to know what the flow rates are, but more critically, what the temperatures are and what the heat exchanges are within the different parts of the plant. And we may observe there that there are certain particularly complex or energy-intensive equipment that we'll need to perform a detailed energy balance for. This, for instance, could be a dryer, where instead of just considering it as a box with energy going in and an initial and final temperature, we might actually look at the processes within it to identify the heat that's being required to raise the input air, to raise the temperature of the material to be dried, to evaporate the moisture from the material, to superheat the water vapor once it's been driven off. And we do that detailed energy balance to better understand these complex equipment, both so that if there is a heat recovery opportunity within that equipment, we can make use of it, but also to identify any potential changes to the operating conditions that we might make that would result in more efficient plant operation or process operation. And that's step 4 of this process. And it's really key that we do this analysis of potential changes to operating conditions before we look at heat recovery potential, because if we make these changes to operating conditions and they improve the energy efficiency of different parts of the plant, then that will consequently limit heat recovery opportunities from those parts of the plant. So we have to consider those first and take those into account before we count on using the heat, recovering the heat from those parts of the plant. Because if our plan is based on recovering heat that then is no longer available because of an operational change, it's a pretty poor plan. The 5th step is pinch analysis. And like I said, I'm going to go into this a little bit more depth in the next few slides. But in brief, it's an identification of all the process streams that need to be heated or cooled, and then the extraction of the critical data associated with the temperatures and the heat that's occurring in the heating and cooling processes. With that extracted data, we can plot so-called composite curves and identify energy targets, so minimum hot and cold utility savings or usage. And finally, based on those composite curves, we can design energy-efficient heat exchanger networks. So make improvements to the existing design or come up with a good initial design. The 6th step is to, based on this analysis, look at the different options that have been identified and to do a pre-feasibility study looking at their costs and their benefits to try and identify which options make the most sense. And based on that, the seventh step is selecting the projects and developing an implementation strategy for executing different projects over a certain planning horizon. So let's go back and look at this fifth step, pinch analysis, in a little more detail. What is this pinch analysis? Well, it's a key tool in process integration, and it's key because it allows all heat exchanges within an entire plant to be communicated in a single graph. So that's very powerful. In that single graph, we can read off the theoretical maximum heat recovery potential, and we can identify the minimum requirements for hot and cold utility. And by comparing that with our existing use of hot and cold utility, we can identify the scope for further heat recovery. Furthermore, we can identify where critical heat exchange is occurring. The critical heat exchangers, those tend to be around the so-called pinch point, which I'll talk about in a bit. And we can see where heat recovery may make sense, where it'll have absolutely no ultimate net impact on the plant, and where it may in fact incur a penalty. So pinch analysis involves, as a first step, building some composite curves. So this goes from taking your simplified process flow diagram, doing data extraction to come up with a streams table, which is essentially a listing of all the streams, hot and cold, within the plant, the process temperature requirements for the initial and final temperatures of those streams, and then the heat load that's associated with doing that increase or decrease in temperature. And from that streams table, we can construct these so-called composite curves. So let's look at that in more detail. Data extraction, as I said, is finding the data necessary to represent each heat exchange within a plant on a T versus Q graph, so a temperature versus heat graph. I haven't left the R out on heat exchange. I truly mean a heat exchange. It doesn't necessarily have to be in the form of a simple heat exchanger. Lots of different equipment is doing heat exchange within the plant, and we try and find a way to represent all of it on a T versus Q graph. So let's look at how a simple heat exchange would look like on a T versus Q graph. You have a hot fluid coming in at a certain input temperature and being cooled down to a certain output temperature, and it does this. It is cooled down by transferring its heat to a cold fluid that in turn needs to be heated up from its inlet temperature to its outlet temperature. So what's fixed about this are these temperatures, right? These temperatures are fixed by the process, typically. We don't have latitude to change these temperatures. And if the flow rates are fixed, and the CP of the stream is fixed, then that also fixes the duty or the Q. So this difference between this point and this point is fixed by a calculation of the mass times the CP, the mass flow rate times the CP times the difference in temperatures. Note, however, that while the temperatures are fixed, we can shift these curves left and right as we want. It's not the absolute value of Q that has any physical significance. It's the delta Q that has significance. And that's a key consideration, as we'll see in the next slide. So we can't move these curves up and down, but we can shift them left and right. Also, the slope of these line segments is essentially dictated by the values of the mass flow rate and the CP. The slope is essentially the inverse of the mass flow rate times the CP. Now, we can do this for each of the individual heat exchangers within the plant. We can generate a T versus Q graph, and then we can take all the line segments for the hot fluids, the hot streams, and combine them into a single line according to some basic rules that I won't talk about today. And the combination of all these individual line segments is the hot composite curve. It's a graphic representation of all the hot streams in the process. And these are streams that need to be cooled. Conversely, we can take all the cold fluid or cold stream line segments and combine them in a single graphic. And that's a representation of all the cold streams in the process. And these need to be heated. And when we do that, we end up with something that might look a bit like this. So here, the red curve is the hot composite curve. and the blue curve is the cold composite curve. And these are just made up of all the different line segments from the different heat exchangers within the plant. Now, when we place these both on the same graph, we immediately get some really interesting information. Where these hot and cold curves overlap, there's a potential to transfer the heat from the hot curve down to the cold curve, right? I mean, it's hotter than the cold curve, so the temperature permits us to do that. And in terms of delta Q, the same amount of heat is being exchanged. So in terms of heat and temperature, that's a reasonable exchange. Where there isn't overlap between the curves, however, there's no potential for heat recovery. So here, for example, we have this cold part, this part of the cold composite curve that does not overlap with the hot composite curve. So we have to heat this with utility. There's no other choice. And similarly, on this side, we have no overlap. So this part of the hot composite curve has to be cooled with your cold utility. And these are, in fact, the minimum utility requirements for hot and cold. If we perfectly align our heat exchangers, we can achieve this maximum heat recovery between these two lines, but the part that's overlapped does not have overlapped curves, has to be met by hot and cold utility. So immediately that tells us our targets. And that's a really powerful thing to know because it tells us how close we are to achieving a good design. The other important consideration is, as I mentioned, for the individual line segments, we cannot shift them up and down because the temperatures are fixed by the processes. But Q, it's delta Q we're interested in. It's not the absolute value of Q. So by convention, we arbitrarily choose to start the hot composite curve at Q equals 0 and build it up from there. But once we've done that, we can take this cold composite curve and we can shift it left and right. Can't move it up and down, but we can shift it left and right. If we shift it in really close, well, firstly, it can't go to the left of the hot composite curve because then you would have a negative temperature difference between the two and heat flow isn't going to occur. But as you shift it further away to the right, what that means is that there is a larger and larger difference in temperature between the two curves. So there's a greater driving force for heat exchange between the hot and the cold processes. So that facilitates heat exchange, and it means that we can use smaller heat exchangers, so less costly heat exchangers, but it also means that we're going to have more flexibility in how we associate hot and cold streams for heat recovery because there's a bigger driving force across between the two different streams. However, there is a downside to that, of course, and that is as we shift that cold stream further to the right, yeah, it makes it easier in terms of smaller heat exchangers, less costly heat exchangers, but we're increasing the amount of this cold composite curve that is not overlapped by the hot composite curve. So that increases our hot utility requirement. And by the same amount, our cold utility requirement is increased because this is moving this way and this unoverlapped region here is increasing. So there's a natural trade-off between how close these curves approach, which the closer we bring them minimizes the cost of heat exchangers, and our hot and cold, minimum hot and cold utility requirements. So for this particular industry that these are taken from, I'm not sure what this process is from, but a delta T min, that is a minimum approach temperature at the critical heat exchanger where these composite curves are at their closest point. That's called the pinch point. We could read off the minimum hot utility requirement is 850 kilowatts, and the minimum cold utility requirement is 550 kilowatts. And we can compare those with our current utility requirements, and that is then the scope for improvement. So that's interpretation of the composite curves. We can use these composite curves beyond that. In essence, what the pinch point does is it separates the plant into two separate parts. Above the pinch point, there's the part of the plant that's in the heat deficit situation. And above the pinch point, then only heating is required. Conversely, below the pinch point, we're in an excess heat situation. And below the pinch point, only cooling is required. So it's two independent plants, essentially, that we're looking at now. Because why I say they're independent is because transferring heat across the pinch incurs a penalty. See, here I've just added this heat transfer of an increment of alpha heat across the pinch. And in so doing, I've taken heat from the side where we're already in heat deficit and added it to a side where we already have excess heat. So what that means is our hot utility requirement just increased by alpha, and our cold utility requirement just increased by alpha. So that's why this separates the plant into two different problems, essentially, because we never want to have heat exchange occurring across the pinch point. And we can use this rule as well as the other rules that I just mentioned, or observations, to redesign our network, our plant heat exchanger network, to achieve optimal heat recovery. And we can reconfigure the heat exchangers according to these rules and other ones associated with, say, stream splitting. And we start at the pinch point where things are really critical. That's the minimum approach temperature. So we have very little latitude to associate different hot streams with different cold streams, because if we associate the wrong streams with each other, then we're not going to have a matchup of streams that is going to respect the delta T minimum that we're targeting. So we start at the pinch point and then we move outwards, considering first one side of the pinch and then the other side of the pinch. So that's how we can use these curves. Now, someone who's really good at interpreting hot and cold composite curves can actually read a plant design right off the curves. And it's going to be a plant design that achieves really good heat recovery. But it's a really challenging thing to do. It takes a lot of practice to be able to see that. Fortunately, you don't need to be that expert in the interpretation of the composite curves in order to use the information that's in there. That's because there's software available to do it. And one very good piece of software for doing this is Natural Resources Canada's integration software. It's powerful and it's easy to use, which is always helpful. And it does a lot of things, but the three things that I want to show you today are the automatic generation and interpretation of composite curves, the application of a network pinch optimization technique to help us redesign the heat exchanger network. And this is an approach that involves not presenting you with a final optimized design that may or may not make sense in the real world. It's a step-by-step approach that at each step proposes a single change to your existing network that you can then, it proposes a suite of potential changes to your existing network, but each one is just an individual change. And you can pick from among the different options that it's proposing for each individual incremental change based on your engineering knowledge of the process in terms of, what makes sense in terms of how close streams are together in the plant, or whether there might be streams that would react if they were actually in contact. You would not want to be putting them across a heat exchanger. So we can bring our engineering knowledge to the question, to the problem, and adopt the proposed changes that make sense on a step-by-step basis. The third aspect of the software that I want to demonstrate is heat recovery from the utility systems. So this doesn't involve pinch analysis at all, but it's still really helpful to be able to look at common standard approaches to heat recovery from utility systems and quickly see what they would be, say, for steam, refrigeration, and compression. So those are the three things I want to show you from the software today. So the first demonstration is how we can generate composite curves for a ridiculously simple example. That's what we're seeing here. So here we actually don't have any heat exchangers at all. We just have two heaters and two coolers. And we have feed 1 and feed 2 going in. You can see that feed 1, for instance, has to be heated from 20 degrees up to 180 degrees. And that requires 3,200 kilowatts of heating. And we can go through and look at all the other aspects. The first step in this, of course, is to try and extract the data and put it in a streams table. So I could start with what I just said there. Feed 1 is a stream, obviously. It needs to be heated from 20 to 180, and that's going to take 3,200 kilowatts. So here's a streams table. There's feed 1, goes from 20 to 180, 3,200 kilowatts. And I've done that for all the other streams here. So that's kind of the data extraction process. Now I can take that streams table and I can put it into the software. So let me just switch over to the software here. So here's the integration software. This is not a course right now in this webinar where you're going to learn how to use the software. I'm just trying to show you some of its features. So I'm going to take this here, process heat recovery, and I am going to say new project here. And I'm going to give the project a name. The project name might be demo. Click OK here. And then I get an option to enter the streams in here. So I can say this is feed 1. If you might recall, it was going from 20 degrees up to 180 degrees. And that involved a heat load of 3,200 kilowatts. And there I've started on my streams table. Now I could go through and fill all these other streams out. There's only 4 of them, so it's pretty straightforward for this one. There is also another option to import from an Excel file. I could show you that. But actually what I'm going to do for today, just to speed things up, is I'm going to load the completed work from this. So what I've done is I've gone and I've filled out that streams table. So there's my feed 1, 20 to 180, but also feed 2, column feed, and product 2. And what I've also done is I've established my current heat exchanger network based on a streams representation of the process. So these are different streams, right? Here's feed 1 going from 20 to 180. It's got a heater in it, and that heater is got a duty of 3,200 kilowatts. Here's feed 2 going from 140 to 230. It's got a heater in it as well. Here's the column feed from 250 down to 40. It's got a cooler in it. Similarly, product 2, it's got a cooler in it. And just looking back at our design here, we can see that that corresponds to what we had here. Feed 1, feed 2, there's product 2, product 1, or column feed, and there's the different coolers. 2 heaters, 2 coolers. That's what we've got here. So I just loaded that to save a bit of time. What I really want to show you here is when I look in the analysis here, here are the composite curves for that. And here are the interpretation of the composite curves in terms of minimum hot and cold utility requirement, actual hot and cold utility consumption, and the scope for further improvement. So first, let's look here. I can make those bigger here. Here are hot and cold composite curves for this process. This nice editor allows me to explore these composite curves. You'll see that there's a vertical cursor here, and as I scroll left and right, it tells me what streams are contributing to those individual sections of the composite curve, both on the hot side and the cold side. I can change my cursor to horizontal cursor, which can be helpful for picking up the temperatures associated with these different streams. And I can also go over here and I can identify particular exchangers, what are generically called exchangers, although they may be actually heaters as they are coolers in this case, and see what parts of the composite curves are essentially participating in that particular heater, cooler, heat exchanger. I can similarly do that for streams. I can identify a particular stream and see where it is on this composite curve. And the pinch point is right here in the middle, obviously. It's this vertical purple line. So we've got a delta T of 10 degrees across this here. And I can see there's a little bit of section here that there's no overlap. So that tells me that I'm going to need hot utility to raise the temperature of this, and I'm going to need cold utility down here. So the cold utility should be around 1,000 kilowatts, the minimum cold utility requirement, and the minimum hot utility requirement should be around, let's see, it looks like about 600, 700. So when I close this up, I find that also in this results table here. There's my minimum hot and cold utility. It's actually 750 and 1,000 exactly. There's my approach temperature, my pinch temperatures, and here is the scope for further heat recovery, 5,000 kilowatts. So that demo is just to show you how the tool is nice for exploring the composite curves and understanding what you're looking at in terms of your plant. The next thing I want to show you in this software is how we can use the software to actually improve a really simple design. So here's a low temperature separation section of a gas processing plant. Very simple, not optimized design. This is something you could easily figure out on your own, how to improve the heat recovery, but I just wanted to do a simple, quick design optimization to show you how the software works. So we have gas coming in from the inlet compressors. It's hot, 48 degrees. We need to cool it down to minus 35. So obviously a huge cooling requirement, over 5 megawatts. Then we put it through low temperature separation, and we get some vapor, we get some liquids, and then we get ethylene glycol that needs to be regenerated. We need to heat up these low temperature outputs to 38 for the vapor, 34 for the liquids, and 70 for the ethylene glycol. And our utilities are, for the hot side, glycol at 100 degrees Celsius, and for the cold side, some refrigeration at minus 41. So what can we do with that? Well, our first step would be to extract the streams, but we've just looked at that, so I'm not going to do that. And then put in, a cooler here and 3 heaters here into the streams. So I've already done that just to expedite this process a bit. So I'm going to load what I've already prepared for that, and that's this here. So here are the streams data, right? Here's that hot stream that needs to be cooled from 48 down to minus 35, and there's that in excess of 5 megawatt heat load on that. And there are my 3 cold streams that need to be heated up from minus 35. And in a streams representation, this is how the process looks. There's this one hot stream that needs cooling, and I've got a refrigeration system that's doing that. And then I have these cold streams that have heaters in them. Now, this is obviously not the optimal design, so let's see how the software can help us find the optimal design. So we're going to click here to lock the data, which means I'm not going to make any further changes to these heat exchangers right now. I'm kind of locking in the current topology and then saying, based on that, propose for me some incremental improvements in this design. And I'm going to tell it that incremental improvements could include redistributing the load among any existing heat exchangers. Currently, there aren't any heat exchangers in there, but in later steps, there will be. I'm going to let it add heat exchangers. I'm going to let it relocate heat exchangers, and I'm even going to let it split streams. So based on that, I click here, and then it comes up with a list of potential incremental changes to that design that I might consider. So here's the base case, which is the initial design I started with. There's no hot utility savings in that, but here's 3 potential changes. One of which, by adding an exchanger, I can achieve 74% of my potential heat recovery savings. So that seems pretty good. Add one heat exchanger, and I recover 74% of the potential heat that can be recovered. So let's see what that looks like. So I click over here to get a streams representation of that, and I see what it's done is it's simply said, okay, you've got this heat available in your inlet stream. Tie that to the vapor that's going to sales with the heat exchanger and heat it up from minus 35 to 38 degrees. That's as high as it needs to go, so we can completely eliminate the first heater here. Its duty has gone down to 0. So I look at that and says that makes sense. My engineering knowledge says that's a reasonable choice. So I select that change here, and I click OK. And what it's done now is it's based on that original base case design, proposed a slightly modified design. So now I'm going to work from that slightly modified design. I click on that. There's the same streams data, but here's the heat exchanger network. See, that's the heat exchanger network that we agreed to in the last step. And now I'm going to ask it to propose changes to this heat exchanger network. So I go to retrofit options, lock the data, allow it to make all those same types of changes as before, and ask it to generate a few different options for me. And here they are. So once again, it's proposed to add some heat exchangers here. And it's found that a further heat exchanger can achieve 81% of the scope. So we were at 74% of the scope for heat recovery before. Now we can make it up to 81% by adding a second heat exchanger. Well, obviously I'm going to want to look at what it's proposing to do. So I click here, and that particular change is to simply add another heat exchanger, recognizing that we have heat still available in this hot compressed gas. We can extract some of that heat to heat up the low temperature liquids. So I put it in series with that first heat exchanger, and I can then provide 330 kilowatts of heating to this. But you know, I look at that and I say, well, there's still heat available in that stream. I mean, obviously I still need to cool it down using 1.5 megawatts of cooling. So there's still heat available. Why didn't it completely eliminate this heater too? Why do I still need to use 700 and 800 kilowatts of heat in this heater? Well, the answer is here, right? This is at minus 14.7 when it comes out of this heat exchanger. And this hot stream is at minus 4.7 when it comes into this heat exchanger. And for the specified delta T min of 10 degrees Celsius, I can't do any better than that. So it's a temperature requirement essentially there. So this all thermodynamically makes sense. I look at that and I say, well, yeah, okay, that's an okay design. I'm going to accept that. So I click here on this to accept that, and I go, okay. And now I have this remodified design to work with, and I can ask for it to make changes to this one. I'm going to do that now. So what it's proposed this time is not the addition of another heat exchanger, but actually splitting the streams. And by splitting some stream here, it can achieve 99.4% of the total scope. So virtually the entire potential heat recovery can be achieved through this design, which involved the two heat exchangers we just added, as well as splitting the stream. So let's take a look at what that looks like. Okay. So rather than placing these two heat exchangers essentially in series on the stream, it splits the stream in an intelligent way such that there's sufficient heat in this side of the stream to completely eliminate a heater one. So there's enough heat there to heat this one fully. And on this side of the stream, there's enough heat to fully heat this one. So we can completely eliminate heater 1 and 2. And obviously this is a smarter design than what we were just looking at there. I can also look at that on the composite curve by clicking here. So I can, it's a very strange looking composite curve, very parallel. It's not typical, but certain industries that arises. But now I can see here are my different heat exchangers. I can see where they are on this curve. And I can also look at the different streams. So I can also use this to understand the changes it's proposing, as well as looking at the heat exchanger network. Now, in reality, I would certainly stop here. I'm very happy if I've achieved 99.4% of the potential energy savings. But I am going to continue with the example just to show you that it can find the design that achieves the thermodynamic minimum hot and cold utility requirements. In fact, I probably would have stopped in real life after the first step, adding a single heat exchanger that achieved 75% or so of the potential heat recovery. Probably that would be good enough, but this is just a hypothetical example. So based on that last redesign, here, based on this redesign, I'm going to ask it to propose some further modifications. And let's see if it can find the perfect design, 100% heat recovery potential. It has to think through a few different options. My computer isn't particularly fast. Yeah, so when I look at that in terms of percent of scope, I see that, yeah, the addition of one further heat exchanger, and I do achieve the 100% of the heat recovery potential. And that design looks like this. Same split there, but now on this side of the stream, I have two different heat exchangers. So this first heat exchanger provides a minuscule amount of heat for the ethylene glycol to regeneration, and it raises the temperature up to 38 degrees, but then I still need another 12.5 kilowatts to raise it up to 70. There's still heat available. I still got to cool this down, so there's heat available, but it's a temperature constraint, because if we look here, here's 38 degrees, so that's the outlet of this heat exchanger. Here's 48 degrees at the inlet. I'm at the delta T minimum. But that is the optimal design. So you obviously could have found that by hand very easily in this case. But for a more complex plant, or even a slightly more complex plant, it can be quite challenging to identify the optimal design. And the software will help you find it. So the last demonstration, and there's our design that we've just come up with. We saw its representation in the streams form, but when we look at it in this form, it's exactly the same thing, right? Here's the split occurring right here. Talked about here are the two heat exchangers in series on one side of the split. Here's the other heat exchanger on the other side of the split. The third example I want to look at is nothing to do with pinch analysis, but everything to do with heat recovery from a common utility system. So a boiler. So here we have a boiler generating steam for a process, but some of the steam is also being used in a deaerator. So the deaerator has feed water that's 20% makeup water coming in at 10 degrees Celsius, and the remainder is condensate return at 95. And to heat the mixed condensate and feed makeup water up to 110 degrees and strip off anything we need to strip off, and we have some deaerating steam coming in here. So the first thing we might want to ask is, well, I'd just like to know a little bit of information about the basic functioning of the system. For instance, what's my boiler efficiency for these given parameters? How much steam is being used in the deaerator, and what's the deaerator inlet temperature? And then I might also want to know a little bit about opportunities for heat recovery. So, for instance, how much energy is available in the flue gas for heat recovery? How much energy is available in the blowdown? So that's the first part of this. And I have looked at that particular heat exchange, or that particular boiler here, and entered the parameters that appear on that page to come up with an analysis of the operation of that boiler. So for instance, the first question we had for this boiler with this given capacity, steam production, operating pressure, blowdown rate, etc., flue gas, excess air, carbon monoxide. The first question was, what's the efficiency? Well, there's a calculation of its efficiency. Another question was, what's the energy available in the flue gas? Well, there's the energy available in the flue gas, both above and below the dew point. No, that actually appears somewhere else, sorry. And here's the energy available in the blowdown. So lots available in the flue gas if we were able to cool it down to 20 degrees Celsius, an arbitrarily chosen temperature for this, but it gives us a point of reference. And here's the energy available in the blowdown, 538. And some details about that. The other thing was a question about the deaerator. So I've got a deaerator in here. And if I look at the deaerator, I can see at the bottom here that it's actually using 1.84 tons per hour of steam, which is all utility steam, obviously. and the mixed temperature at the deaerator inlet temperature, deaerator inlet is 78 degrees. So the mix of the makeup water and the condensate return works out to 78 degrees. So that's just some basic information about that, about the operation of that steam boiler. Now, another thing I might want to do is say, okay, well, I've got some heat recovery opportunities. Blowdown heat recovery is pretty easy. Let's see what we can do there. So let's change this same thing, this same system, and put in a flash tank here. Put the blowdown into the flash tank, recover some flash steam, and reduce our utility stream requirement for the deaerator by using this flash steam. And then with the liquid, put it through a liquid-liquid heat exchanger and preheat the makeup water. And we're going to set the goal of heating that up to, say, 40 degrees Celsius. We want to know if that's possible for this plant. So let's see what we can do there. And of course, we want to compare that with the base case, which we just looked at, and see, what's the steam savings in the deaerator, what's the savings due to blowdown heat recovery, and what's the maximum temperature after heat recovery, both here and here. So the software can help us do that. First thing is, I'm essentially taking this base case and making a few minor modifications to it. So I'm going to copy the base case over to the proposed case. And then I start off with two identical systems. So I look at the bottom here and I see the difference between the two in terms of their key parameters is 0 because they're identical. What I want to do is I want to add blowdown heat recovery to this proposed case. So I go over here and I pick up one of the different options for heat recovery. So I have options like condensing economizer or flash recovery or other options. I'm going to pick blowdown recovery, give it a name, and associate it only with the proposed case. Click OK. And here's parameters associated with the blowdown heat recovery. It's associated with my steam boiler here. Key thing here is flash heat recovery. Currently, steam is not recovered, but in fact, I want to recover this steam and send it to the deaerator. So that's an option right here. So I click there, and then I have to tell it which deaerator. I've only got one in this particular case, but I could have more, in which case I'd have to specify one. Not only am I recovering the flash steam, but I'm also planning on recovering heat from the liquid. So I click there to say that I want to do that. And then I say, which stream am I exchanging that heat with? I could add a process stream here, but in fact, I want to add it to the makeup water. I want to preheat the makeup water. So I click there. Okay. And it gives me this form, which allows me to specify where exactly I'm adding this. So for instance, on the base case, I've got makeup water at 10 degrees, which I said, condensate return at 95, and then the mixed temperature is 78 degrees when I combine those two. On the proposed case, I want to take that makeup water, add this blowdown heat recovery there, and it tells me that actually with the heat available, I can achieve up to 43 degrees Celsius. So I said I only wanted to achieve 40, so I put in 40 there, and then when I look, the mixed temperature is now 84. So instead of coming into the deaerator at 78, it's coming in at 84 because of this blowdown heat recovery. Now that's from the liquid heat recovery, but I'm also recovering steam, flash steam, essentially. So if I go and I look at the deaerator here, I see that before, in the base case, I was using 1.84 tons per hour of steam, of which all was coming from the utility system. And now I only use 1.47. And that reflects that the temperature of the inlet water to the deaerator is now at 84, not 78 like it was before. So I need less steam. And furthermore, about a third of it is coming from recovered steam. So this is that steam that I'm getting from the blowdown flash steam. So that's the impact on the deaerator. The other thing that I see here is on the blowdown page, The heat recovered is 266 kilowatts from the flash steam and 211 kilowatts from the blowdown water. So I'm essentially saving, 477 kilowatts between the two of them. And that's obviously going to have an impact back on the steam plant. And here's that impact. Efficiency hasn't changed at all because the operating parameters are the same, but we need less steam. So that ends up with impacts for the annual fuel costs and for CO2 emissions. So that's shown here. So that's the third demo of the software. Nothing to do with pinch analysis there, but it shows how you can have this very nice set of calculators for looking at the operation conditions of common utility systems and quickly assessing heat recovery potential from those utility systems. So the next steps might be that you look at the software and you say, wow, that looks pretty good. I'd like to get that. And there's good news. The software is available to you and it's free. It's free, but exclusively to Canadian industry. So Natural Resources Canada developed this software. Obviously, it's powerful software. It required a lot of engineering analysis to develop code. So they want that benefit to flow to Canadian industry. Their only requirement is that they want the software to be used intelligently, because any software, if used in a foolish way, will generate foolish results. So they're requiring a minimum level of training for using the software, and that's a 3-day training course. In the past, when we've given these courses, it's been 2 days focused on the process integration and 1 day on utility systems heat recovery. The course involves hands-on exercises using the software, as well as, of course, discussion of process integration approaches and theory. And the training also involves a brief mention of what incentives programs are available through Natural Resources Canada and other provincial governments and utilities. So there is training available for this software coming up. It's in Vancouver, April 5th to 7th. I will be one of the instructors. The other instructor will be Dr. Alberto Alva from Process Ecology. Alberto did his doctorate in process integration at the University of Manchester. He has, I guess, about 20 years of experience in process integration, so he's a very valuable addition to the course. The course costs $1,400 plus GST. In the meantime, I'm providing more of these introductory webinars, so if you think you know someone, a colleague or a client who would be interested in getting a little bit of an introduction to process integration in this software, the next webinar is going to be at this same time on March 15th. For more information, either about the training or the webinar, you can visit this site on my web, or you can register by emailing me at that address. You can register for either the webinar or for the 3-day course. So that's michael.ross@rerinfo.ca. If you have any questions, I can try to answer them now. You're probably muted, so you'll have to unmute yourself. But if you have a question, feel free to put it out, and I will either be able to answer right away, or if not, I will get back to you by email. Any questions or comments? Yep. Yes, I can hear it. That's Andrew Cooper.
Yes, correct. Yeah. So, quick one. We have a mine here, so our process doesn't have any heat applicable as such in the milling process, but we have waste heat coming from our mine in terms of our ventilation shafts.
Yeah.
It's very hot, but we heat the air going underground in winter. Would this be able to allow us to determine what's recoverable and what's reusable in terms of we can make best use of that heat coming out of the mine to heat the air going into the mine?
In theory, yes, but I haven't done that particular exercise, so I can't guarantee that it would work out. But definitely heat recovery from what we call effluent streams is part of this. So when we were looking at these examples here, the temperatures were all essentially fixed by the process. We had to heat the the cold streams from a certain starting temperature up to a certain final temperature, and conversely, the hot streams had to be cooled down to certain final temperatures. When you're dealing with something like effluent streams, which might be the case in your mind. I'm not sure if I understand the situation correctly. There's no requirement for the final temperature of the stream, but nevertheless, it's heat that's available. So you can see if there's an opportunity to make use of that somewhere. So the software is pretty flexible. I think that it might be possible to do that analysis. I just haven't done it, so I can't guarantee you that it's possible. But if you sent me more information, I could try and get a better answer for that. Any other questions or comments? No? Well, if you do think of questions or comments, feel free to email me or contact me otherwise. I'd be very happy to try and answer those questions, or if I can't answer them directly, to get more information and to try and answer them. I don't have anything else for this webinar, so if there are no more questions or comments, I will wrap up here. So I guess that's, oh yeah, is there?
Yeah, I was just going to say, Michael, I got to run because I'm
okay
in between meetings right now. But thanks a lot for that. And somebody just posted a question here, whether you provide your PDFs of your slides or anything like that.
Oh, I didn't even see the question. Sorry. Yeah, actually, I haven't thought that through. I certainly plan to post this presentation, like the recording of the presentation, which will include the slides. For posting the PDF, I will look into that. I have to find out if Natural Resources Canada would be fine with that, because I've used some of their materials on here. But if they are, sure, yeah, I would post the information from these slides.
Okay, thanks. I'm going to log off.
Okay.
So it was, yeah, you look down below in the chat and you'll see Sean and Quinn asking Sean asking a question about the PDFs. But yeah, okay, cool.
I got that.
Thanks again. We'll chat soon.
Thank you very much. And in that case, I guess thank you to all of you for attending this. If you are interested in any further training opportunities, please let me know. And if there's any questions, also please let me know.
Thank you, Michael.
Thank you.